This paper presents the results of the application of thermally activated cobalt-iron hydroxide as photocatalysts. Hydroxide were obtained by co-precipitation with cobalt-iron radius 1, 2, 3, and 4. Hydroxide were characterized by X-ray diffraction, infrared spectroscopy, thermal analysis, neutron sorption, and scanning electron microscopy with dispersive ray energy. In recent years, the presence of recalcitrant organic pollutants in water bodies has increased significantly, affecting the ecological balance. These compounds are characterized by their high toxicity and stability in the environment, so achieving their complete degradation is one of the research priorities worldwide. Within the families of recalcitrant toxic aromatic pollutants, phenols are a priority considering they are widely used by a variety of industries and domestic applications. Specifically, 2,4,6-trichlorphenol is considered a potentially carcinogenic contaminant. Among the main techniques developed of the degradation of recalcitrant organic compounds is oxidation, which employs agents such as peroxide, ozone, and chlorine dioxide, generating toxic solutes, dangerous reaction products, or high energy cost. To avoid this operational disadvantage, photodegradation techniques have been developed using semiconductor materials that are characterized by degrading aromatic contaminants efficiently to mineralization. A family of compounds that have aroused interest to be used as photocatalysts with hydroxide-type materials, which are structurally composed of inorganic layers that are chemically characterized by the general formula, where M2 plus is a divalent metal and M3 plus are divalent cation with which octahedral networks with positive residual charge are structured. A and less are anions that are housed in the internal laminar space to compensate for the residual charge of their sheets, and M is the number of molecules of water. The objective of this work is to find a process of degradation of 2,4,6-trichlorphenol using a photocatalyst for water decontamination activated hydroxide of different cobalt-iron radio, which is more efficient than using uh, titanium dioxide. The hydroxide cobalt-iron was synthesized by co-precipitation at pH 11.5 of a solution of cobalt nitride hexahydrate and iron nitride non-hydrate with an alkaline sodium of sodium hydroxide. The cobalt-iron photocatalyst was obtained by calcining the precursor at 500 Celsius degree for 4 hours. A standard solution of 80 ppm of 2,4,6-trichlorphenol was placed in a batch reactor at a controlled temperature of 25 Celsius degrees. Constant magnetic stirring of 700 rpm, airflow of 1 milliliter per second, light irradiation UV of wavelength 255 nanometers, and an emission of 2.5 milliwatts, generated by a pen-rail UV lamp inserted into a quartz tube. Prior to UV irradiation, 200 of the catalyst was connected with the standard 2,4,6-trichlorphenol solution for a period of 1 hour in the dark to verify an absorption-desorption equilibrium of the contaminating molecule with the catalyst. Once the equilibrium has been researched, irradiation begins for a period of 3 hours. In addition, commercial titanium dioxide was used of comparison against a reference photocatalyst. In all cases, the process of degradation of the contaminant was monitored by sampling aliquots of the reactor with the subsequent quantification of this in a Curie 100 UV spectrophotometer at wavelength of 311 nanometers. This figure shows the direct patterns of the total hits of different cobalt to iron radios activated at 500 Celsius degree. Observing for all catalysts, the signal corresponds to the JCPDS card number 421467, corresponding to the diffraction pattern of the cobalt tetraoxide with structure cubic. The thermograms of the high total hits of the differential thermal analysis (DTA) and of the thermogravimetric analysis (TGA) are in this figure. With respect to DTA, it's observed that the different cobalt-to-iron precursors have a similar thermal evolutions corresponding to the signals of the dehydroxylation of the molecules used in the interlaminar at 300 Celsius degree and the total decarbonation and dehydroxylation at 680 Celsius degree. Additionally, the hydroxylates HTM3 and HTM4, an additional reaction at 998 Celsius degree associated with the crystallization of the cobalt-30 spinel. In relation to the loss of the weight, as can be seen, the precursor HTM2 presents a fierce weight loss associated with the elimination of water around 200 Celsius degrees, since it decreased up to 12% of its original weight, while the HTM3 and HTM4 samples have a similar weight loss of 3.5%. The second weight loss occurs between 600 and 700 Celsius degrees, which for the solid HTM1 contributes with a loss of 22%, the HTM2 of 33%, the HTM3 of 34.5%, and the HTM4 of the 46.5%, being related the one with the greatest loss, total research losing 50% of its mass up to 1100 Celsius degrees. The photoluminescence spectra of the activated hydrotalcids at 500 Celsius degree are shown in this figure. Photoluminescence studies were performed for the synthesis materials as shown in this figure to corroborate the facility of recombination of the electron holes photogeneration spaces, since it's a key factor in photocatalytic processes. The sample labeled as ATM1 showed the highest intensity of photoluminescence compared to the rest of the materials, around 465 nanometers, when it's excited at 294 nanometers. This behavior indicates a high rate of recombination of the photogenerated per electron hole. However, the intensity of photoluminescence increase in HTM2 indicates a low rate of recombination of the charge carriers. This result is consistent with the photocatalytic behavior, since it was the one that presented the highest photocatalytic efficiency. The decrease in the recombination rate is due to the transfer of the photogenerated charge carriers. This figure shows the graph of the relative degradation rate of 80 ppm of 2,4,6-dichlorphenol with the different catalysis. It can be that photocatalysis shows a good degradation of 2,4,6-dichlorphenol at 90 minutes, researching 85% for HTM2, 58% for HTM1, 50% for HTM3, and 33% of HTM4. The above indicates that the most efficiently catalyzing the degradation of 2,4,6-dichlorphenol is the HTM2, corresponding to a cobalt-to-iron ratio of 2, showing better activity during the entire iteration time. This table shows the kinetic data of the Sayeti constants and the half-life of the photodegradation process of 2,4,6-trichlorphenol. The kinetic data confirm that the HTM2 catalyst is the one with the best activity by showing a weighted kinetic constant of 71 minutes and a half-time of 28 minutes. With respect to the catalyzed HTM1 and HTM3 have the same kinetic constant and with the lowest activity with only 33% degradation. And this figure show the adjustment of the kinetic model of the relative degradation rate of 80 ppm of 2,4,6 trichlorphenol with the difference catalyzed, which corresponds in all cases to a degradation behavior of pseudo-first order, considering the steady state condition corresponding to the kinetic model of Lagrange-Hirscher. In last time, the activity hydrolyzed at 500 Celsius degree from a mixture of the crystalline cubic simple oxide and amorphous cobalt to iron mixed oxide load carriers due to the transfer of photogenerated cargo carriers, which produce a higher photodegradation capacity of 2,4,6-trichlorphenol, reaching 65% and a rate of 1 milligram of catalyzed of solution at a concentration of 80 milligrams per liter. Thank you very much.